What is QuickSort? QuickSort is a sorting algorithm. QuickSort uses divide and conquer. It splits a list. Divide and conquer more generally though is when you break a problem down into smaller subproblems and then solve those subproblems. Some other examples of divide and conquer are merge sort and the Karasuba algorithm. QuickSort is also recursive. Doing QuickSort on a list is the same as splitting the list and then doing QuickSort on the sublists. And then likewise, doing QuickSort on those sublists is the same as splitting those sublists and doing QuickSort on all of those sublists. Let's have a look at QuickSort in Haskell. Why is QuickSort so beautiful? I'll show you. Here's the code. So, QuickSort is a recursive algorithm in Haskell, right? The base case is when you QuickSort of an empty list. Sorting an empty list, that's already sorted. That's defined as sorted. So you just return the empty list. Otherwise, when you match a non-empty list, where you match X and then some other list, right, being X's, you then perform QuickSort on that list. You split the list. What does this do? Well, it splits the list into a left and right sections. It does QuickSort on the left section, and then it does QuickSort on the right section as well. As well as that, it then takes the first element and puts it in the middle. This QuickSort implementation finds the pivot, which is this X value, as just the first item in the list. So I'll explain what this means in a minute, but I'll just go over an example quickly. Okay, X would be 1 in this case because it's the first item in the list. The rest of the list, X's, would be this. So let's have a look. What's left? Well, left, right? If we go here, left is the list of everything less than or equal to X, and right is the list of everything greater than X. That means you would have a list here of everything less than X. So this is X, you'd ignore this is greater than, this is greater than, this is greater than, this is greater than, this is less than. So because 0 is the only one less than, that goes into the left list. We then concatenate it with X in a list, and then to find the right list, that's everything else, right? So that's 4, 2, 3, 6. Okay, brilliant. So then you call QuickSort on left. Well, QuickSort on left, right? QuickSort of 0. X would be 0, then the rest of the list is the empty list. So you do QuickSort on left and right. That would then result in this, QuickSort of 0, plus this, and then plus QuickSort of this, right? Well, QuickSort of 0 in a list is the same as QuickSort of the empty list, plus 0, plus the empty list. Now, again, that's plus 1 from before, and then QuickSort of the other side, so that's plus QuickSort of this list here, right? And what that will do is X will be 4 in the first case, so then left will be everything smaller than that, so you have QuickSort 2, 3, plus 4, plus QuickSort of what's greater than, which is 6. Okay, this keeps getting bigger, and we'll be copying this out, right? So it keeps getting bigger essentially. What have we got left to do? Well, we've got to do QuickSort of this. So this will be replaced with X will be 2, right? And left will be the empty list, and right will be just the list of 3. So that will be the empty list, because there's nothing less than 2 in that list of 2 and 3. Plus 2, plus QuickSort of 3. Okay, and then we just have QuickSort of 6 here. So QuickSort of 6 will be, there's nothing smaller than 6, because there's nothing else in the list, right? So that's the empty list, plus 6, right? Plus the empty list again. Okay. So finally, we only have one QuickSort left, and we will do QuickSort of 3. Well, there's nothing less than 3 in the list of 3, and there's nothing greater than 3 in the list of 3. So that will be the empty list, because there's nothing left, plus 3 in a list, plus another empty list because there's nothing greater than 3. Just one thing to point out. All of these empty lists, you're technically calling QuickSort on all of these. However, because QuickSort of the empty list is defined as the empty list, I haven't explicitly said that. But you can see that on line 16, right? Okay, so then what does this result in? Well, this results in the list 0, 1, 2, 3, 4, 6. And this is the sorted list. So that's how QuickSort works. Now, back to this where clause. What's this where clause do? Well, essentially what you're doing is you're kind of defining variables left and right here, right? And you're using it so that you don't have to write this whole thing here, right? You can though. This is essentially what it's doing, right? If I were to do this, then I wouldn't have to have the left and right in. I could just have this instead. And then I wouldn't need these two lines either. However, I think it's nicer without that. I think it's nicer to have it with the where clause and have the left and right. because I think that's more readable now. One final thing to note, is this really a true implementation of QuickSort? When I was researching for this video, I looked into it and I found that some people talked about this not being a real implementation for QuickSort. You can see the full post here, which I'll link in the description as well. But some people talked about it doesn't really use the partition of elements in place, or it's not obvious that it does that. I'll link a Stack Overflow post about this in the description, and I recommend you all look at it. It's very interesting. Thank you very much for watching.